We'll continue from where we stopped in the last class. Okay. So let me PR has been. Okay. We'll continue from where we stopped in the last class. So we have discussed most of the classification of signals in the last class. 1 second. Now today we'll discuss the other classification, which is energy and power signals. This is a very important classification because we need to learn a lot of things from this part. So we'll be sending some time here. Okay. So next classification is energy and power signals. Okay. Right. Now, to evaluate the energy of a continuous time signal, the relation to evaluate the energy is given by energy is equal to integrate over the whole range, integral minus infinity to plus infinity, mod x of t square dt. Okay. In the case of real signals, this mode is not very important. For complex signals, actually this relation is x of t into h star of t. Okay. For complex numbers, z into z star implies z into complex conjugate of z, that is mod z whole square. That is why actual relation is x of t into x star of t. That is why it is coming mod x of t square dt. Okay. Right. Reshma, your audio is not muted. Please mute. Reshma Ranati. Please mute your audio. Okay. Right. Reshma, are you able to hear me? 1 second. Okay. Right. So this is the relation for energy of a. This is the relation for the energy of a signal. Energy is given by integral minus infinity to plus infinity mod h of t square dt. Now, this implies if you have a signal, suppose as an example, I'm taking the signal e raised to minus at into u of t. Okay. So this is a signal which is existing from 0 to infinity because u of t is there. Naturally, the energy can be evaluated as E is equal to integral. I need not go from minus infinity to plus infinity because the signal is existing from 0 to infinity alone. So that is integral 0 to infinity. Then I need not write u of t because u of t is 1 in this particular range. So what is left out is e raised to minus at. If I square that, e raised to minus at whole square, correct, dt. This will be the equation. Now that is equal to integral 0 to infinity e raised to minus at into e raised to minus at, that is e raised to minus 2at dt. Right. Now the integral, if you do the integral part, the integration of e raised to minus 2at is e raised to minus 2at whole divided by minus 2a, whole divided by minus 2a, correct? And limits are infinity and 0. So if I apply the upper limit, e raised to minus infinity becomes 0, minus 0 if I apply, that becomes 1. So 1 by minus 2a, correct? So minus and minus will cancel out and the answer will be 1 by 2a. So this is the energy of this particular signal. Okay. That is the energy of that particular signal. Now, whenever the energy of a signal is finite, okay, whenever the energy of a signal is finite, if the energy is finite, then it is called as an energy signal. Okay, this is an important definition. If the energy of a signal is finite, you can term it as an energy signal, right? So we'll find the energy of another signal now. Do you want to take down this? This is the energy of a signal. If it is finite, then we call it energy signal. Is it clear to all of you? Should I wait for some time? Do you want me to wait? Yes or no? No. Okay. So I'm moving forward. Okay. So this is the energy of a signal. Now suppose I have a signal like this, right? How do you find the energy of this particular signal? This is a particular signal. Let us mark it as 0, 1, 2, and this is 1. Okay. So I'll tell you how to evaluate the energy for this particular case. See, this line equation, I know. What is that? The slope of this is 1 because opposite side is 1 and adjacent side is 1. So this line will be y is equal to, sorry, x is equal to, y is equal to t, correct? Y is equal to t for 0 to 1, right? And what will be the equation for this particular line? This particular line, I know the slope is negative because it is coming down. Slope is negative and y-intercept is, general relation is y is equal to mx plus c, where c is the point where the line cuts the x-axis. Okay, c is the point where the line cuts the x-axis and m is the slope. And this is time axis, so x becomes t. Okay, so negative slope minus 1 is the slope, so minus t plus y-intercept is, if I extend this line, it will touch 2. Okay, so y-intercept is 2. So this is the relation for t in between 1 and 2, correct? So this is the equation for the given graph. Now I need to find the energy of the signal. Let us see how to evaluate the energy of the signal. First, I'll take the energy from 0 to 1. Okay. In fact, I need to take integral 0 to 2 mod x of t square dt. I'll actually split it into two parts, 0 to 1 and then 1 to 2. Because 0 to 1 is one waveform and 1 to 2 is another waveform, right? So 0 to 1, the equation will be t, correct? So I'll take t square dt plus 1 to 2, the equation will be 2 minus t. That is the equation of this particular line. That is 2 minus t whole square dt. Correct? So if I integrate this, it becomes t cube by 3 limit 1 0 plus 2 minus t whole cube by 3 into or divided by, actually divided by minus 1 because this is minus t. It's not t. So I need to write divided by minus 1, correct? So that limit I need to apply from 2 to 1, correct? So what will be the answer? Here it will be 1 cube by 3, so 1 by 3, right? Plus here it will be, if I put 2, t equal to 2, that will be 0. So 0 minus, now 1 if I put, what will be the answer? 2 minus 1 is 1, 1 cube divided by 3 and a negative here. So 1 by 3 into minus 1, correct? So this will also be negative into negative is plus 1. So answer will be again 1 by 3. So you can see both part is having same energy and the total energy is 2 by 3. So the energy for this particular signal is equal to 2 by 3 and it is an energy signal. Why it is an energy signal? Because why is it an energy signal? Because it is having a finite energy, correct? If the energy tends to infinity, you cannot say it as an energy signal. But here, energy is finite, so it is an energy signal. Now, I just took this problem to tell you one more thing. Actually, I need not evaluate the energy for the second part. It is always going to be the same for this particular shape. That is the idea we need to learn. For example, if I take this particular triangle, okay, see, 0 to 2, 2 to 4. If 0 to 2 is same part is repeated with mirror image on the other side, actually this part energy and this part energy will be same. So I just need to consider the energy of this part and multiply it by 2 to get the total energy. This is applicable only if you have a symmetry about some axis. Here along this particular axis, along this particular axis, it is symmetric. Along the axis x equal to 2, it is symmetric, correct? If you have any symmetry for a particular figure, then you can easily evaluate the energy by simply taking twice. For example, suppose I consider I want to find the energy of this particular signal. Okay, this is a trapezium. Let us say this is -3, this is -2, 0, this is 2, and this is, let us say, what is this? 3. This is a symmetric figure. If I want to find the energy of this particular figure, you just need not take from minus 3 to plus 3. Instead, you can just take from 0 to 3 and take the double. Correct? That part is applicable for any symmetric figure, even if the axis is not y-axis. Here it is about y-axis, but here it is about the axis x is equal to 2. So if you have symmetry, you can utilize this property to find the energy. Is it clear to all of you? So the energy for this particular problem is actually 2 by 3. Is it clear? Shall I proceed? Do you want time to write down? Okay, it's clear. Do you want time to note it down? No need, right? Okay, so I'm proceeding. If you have any doubts, you can unmute and ask. Okay. Someone is trying to join. Okay. Right. So next is about power of a signal. Okay. So next is about power of a signal. Now the definition for power of a signal is given by power is equal to total energy divided by total time. Total energy divided by total time. Okay. Now you know energy is given by the definition. Energy is equal to integral minus infinity to plus infinity mod x of t square dt. Correct? So this term, if it is finite, if this term is finite, then we call it as energy signal. Okay. Now, what is total time? Total time is always from minus infinity to plus infinity, which means the denominator term will always be infinity in this expression, right? If the denominator is infinity and the numerator is finite, in the case of energy signals, it is going to be finite, correct? For energy signals, numerator will be finite term and denominator will be infinity. So power will be, what will be the power for energy signals? Power of any energy signal will be always 0 because you have a finite number divided by an infinite number. Correct? This will always give you an answer of 0. Anything finite divided by infinity is always going to be 0. Correct? So for all energy signals, power is 0. So that is an important point. For all energy signals, power is equal to 0. Okay, for all energy signals, power is equal to 0. It simply comes from this condition because energy signals means energy should be finite. Anything finite divided by infinity will be 0. Naturally, power will be 0. So when will you have a power, a non-zero term? Power will be non-zero if and only if you have numerator part is equal to infinity, correct? Because when you have something called as infinity by infinity, what will be this relation infinity by infinity? You know what is meant by, what will be the answer for infinity by infinity? Infinity by infinity could give you 3 different answers. It could be 0, it could be infinity, or it could be a finite value constant k. For example, suppose I take e raised to t divided by t, limit t tending to infinity. Okay. Numerator is going to infinity, denominator is also going to infinity. What is the answer? Can anybody tell me what is the answer for e raised to t divided by t tending to infinity? Can someone give the answer for this? It can only have 3 different answers. One is either it is 0, or it is infinity, or it is a constant. There are only 3 possible answers for this. Either 0, infinity, or k, any constant. Under which class will this particular problem fall? Can someone tell me? It's 0, infinity, infinity. Okay, so what determines the answer for this is, you just need to check numerator is going to infinity, denominator is also going to infinity. So we need to check which function is going to infinity at a faster rate. Okay, which function is going to infinity at a faster rate? the order of this particular function is, if you expand it as a polynomial, the order of e to the power any function, e to the power t, is always infinity. But the order of this function is 1, correct? So naturally, numerator is going to infinity at a very higher rate compared to denominator. Under that case, this ratio will always be infinity. Now, if the reverse happens, that is, if you consider t divided by e raised to t, here numerator is going to infinity linearly, but denominator is going to infinity at an infinite order, which means here denominator is going to infinity at a faster rate. Naturally, the answer will be 0. Now you can have another case where numerator and denominator are going to infinity at the same rate. Here 3t by 40, if I consider 3t by 40, numerator is going to infinity at a linear order or first order polynomial. Denominator is also going to infinity at a first order as a first order polynomial, which means both numerator and denominator are going to infinity at the same rate. Now you can have the answer for giving a constant value, correct? So actually, when you are finding the limit, you might have heard about L'Hospital's rule, correct? You might have heard about L'Hospital's rule. L'Hospital's rule is actually checking which see what you do in L'Hospital rule. You will differentiate numerator and you will differentiate denominator. When you differentiate a function, you are getting the rate of change of that function, correct? So if you differentiate numerator and if you differentiate denominator, actually you are checking the rate of change of that particular function, right? If you check the derivative, you can see which function is moving at a faster rate, and you can decide. That is what we are doing in L'Hospital rule. So this is a thumb rule in finding out the ratios of infinity. This is considered as indefinite cases, indefinite limit. So we need to go for differentiation. Now we have introduced this maths idea to learn about what are the possible values of power. Power can be 0, power can be infinity, and power can be a constant value, correct? And for all energy signals, power is equal to 0. So when you call as a power signal, a signal as a power signal, that is the next point. We know if energy is finite, then it is an energy signal, correct? Then it is an energy signal, and power will be equal to 0. Power is equal to 0. If power is equal to finite, then it is called as a power signal. Okay, then it is called as a power signal. And for a power signal, what will be the energy? Can someone say for a power signal, what will be the energy? Energy will be infinity. For a power signal, energy will be always infinity. Okay. Now, power can be a non-finite term. For example, power can be infinite. All other possibilities are there. So we cannot classify it as either energy or power signal. We cannot classify it as energy or power signal. So this is a fundamental thing which you should remember. Energy is equal to finite means it is an energy signal. Power is equal to finite means it is a power signal. Okay. For an energy signal, power will be 0. For an energy signal, power will be 0. For a power signal, energy will be infinite. Okay. So for a power signal, energy will be infinite. For an energy signal, power will be 0. Right. Now we'll see how we can evaluate the power of a signal. We have introduced the concept of power as total energy divided by total time. So this should always be kept in mind. Okay. So we'll see the definition for power. Power of a signal is evaluated as power is equal to, we'll take the limit t tending to infinity. I'll take minus t by 2 to plus t by 2 mod x of t square dt. Okay. So what actually is giving you, this relation is giving you the energy, correct? If you think about a time instant minus t by 2 to plus t by 2, right? I'm taking the signal in this part alone, and I'm finding the energy of this signal in this part. Then I am extending this t by 2 to infinity, this t by 2 to infinity by this limit, correct? So it is actually minus infinity to plus infinity, which means this is giving me the total energy, correct? Now I need to divide by t to get the power. So now this is, see, this should be, actually this should be learned as minus t by 2 to plus t by 2 mod x of t square whole divided by t and limit t tending to infinity. So this is actually, numerator is total energy and denominator is total time. So this is the relation to evaluate power of a signal. Okay, this is the relation to evaluate power of a signal. I hope you have written it down. Shall I proceed? Now, next point is all periodic signals are power signals. Okay, all periodic signals are power signals. I'll take an example. We have learned what is meant by periodic and non-periodic case. Okay, so in the case of power signals, there is a simplicity in evaluating the power. You just need not consider the case of this limit t tending to infinity, because for a periodic signal, for example, suppose consider a periodic signal like this. I'll take a periodic signal like this. Okay, this is a triangular wave. It is extending from minus infinity to plus infinity. So this is 0. Let us say this is 2, 4. This is 6. This is 8. I'll take the amplitude as 1. Okay, so that is a periodic signal. Now, if I consider the energy of this signal in this part, that is the same energy in this part also, right? So if I consider the energy in one period as E1 and divide by that period T1, this thing, if I add to total infinity, all the energies are added, that will be actually total energy, right? So if I add that by n times E1, that is divided by n times t also, because n times t1 also, correct? Because every part is having the same period, which means I can actually cancel out this and find this ratio. So for a periodic signal, you need not take this t tending to infinity part. For a periodic signal, power is given by 1 by t integral minus t by 2 to plus t by 2 mod x of t square dt. Why is it so? Because this part gives me the energy in one period divided by one period. Energy in one period divided by one period is equivalent to total energy divided by total time, because the pattern is repeating from minus infinity to plus infinity. So I just need to take this equation to evaluate the power of a periodic signal. Also, all periodic signals are power signals. Okay, all periodic signals are power signals. Is it clear? Any doubts? Any doubts to you? Nothing. Shall I proceed? Yeah, it's clear, right? Okay. Okay, we'll consider the case of a periodic signal first. Okay, I'll take an example. I'll take the example of, let us say, a sine 2 pi t. We have seen the period of this signal. What is the period of that particular signal? Period of that signal is 1 second. We have evaluated the period of a sine omega t or a sine 2 pi t in the last class. It will turn out to be 1 second, because 2 pi into small t plus capital T, correct? That should give me, so sine of 2 pi into small t plus capital should give me sine 2 pi t itself, right? Now comparing 2 pi into capital T equal to 2 pi, because sine of theta plus 180 or 2 pi is sine theta. So I'll get t equal to 1 second. Okay. So this signal is having a period of 1 second. Now, as per our relation, period P is, power P is equal to 1 by period integral over minus t by 2 to plus t by 2. Actually, you need not take minus t by 2 to plus t by 2. Any particular period is enough. It can be from 0 to t, it can be from t to 2t, or any period. It's for its easier purpose. For easier purpose, we take it minus t by 2 to plus t by 2. But you need not take minus t by 2 to plus t by 2 always. You can always take 0 to t or t to 2t, whatever it is useful, helpful. Okay. Now, mod x of t square, which means I'll have a sine 2 pi t square, correct? A sine 2 pi t square dt. That is equal to 1 by, I know capital T is equal to 1, so I'll put 1 here. Integral 0 to capital T is 1, so I'll put 1 here. A square into sine square 2 pi t, correct? dt. A square into sine square 2 pi t dt, which is equal to 1 by 1 is 1, so I'll neglect that. Integral 0 to 1. A square into, I can write sine square theta is equal to, see, sine square theta you can always write it as, if you remember the relation, trigonometric relation, sine square theta is equal to 1 minus cos 2 theta whole divided by 2, and cos square theta is equal to 1 plus cos 2 theta whole divided by 2. Okay, so if I apply that particular property, I can write this as 1 minus cos 4 pi t whole divided by 2 dt, right? So a square by 2 can be taken out. A square by 2 is taken out into, what is left out is 1. Integral of 1 dt is t minus cos 4 pi t integral is sine 4 pi t divided by 4 pi. Okay, cos 4 pi t integral is sine 4 pi t divided by 4 pi, and the limits are 1 and 0. So if I apply the limits, it will be a square by 2 into 1, so that is t is equal to 1, minus sine 4 pi is 0, correct? So that is 0. If I put limits 0, all the terms will be 0. So the other things I need not consider. So the answer is going to be a square divided by 2. So this is the power of a sine wave. Now this is applicable. Now this you can learn it as a thumb rule. For any sinusoidal wave, irrespective of the period, the power is going to be amplitude square by 2. Because you can see in the power expression, there is no 2 pi or period term coming up. Only term which is coming up is amplitude. So for any sine wave or cosine wave, this is applicable. So I'll write that as a point. For any sine wave or cosine wave, for all sinusoids, power is equal to amplitude square divided by 2. Whatever be the frequency or period, it does not depend on frequency or period. It only depends on the amplitude. The power is going to be a square by 2. Is it clear? Shall I proceed? If it's clear, I can proceed. Yeah. Right. I think you have noted this down. I'm changing the slide. Now, one more important thing which we need to learn from this power is, you might have learned about the RMS value of a signal, or root mean square value of a signal. Root mean square value. It is also called as RMS value. Now, RMS value of any waveform is equal to the power of the waveform whole to the power 1 by 2, or that is the square root of power of the waveform is what is giving you the RMS value. Okay, so I can write the relation in another format also. RMS value equal to square root of, now what is the expression for power? Power is 1 by t integral minus t by 2 to plus t by 2 mod x of t square dt, right? This is also an expression for RMS value. So RMS value of a signal is square root of power. So what is the RMS value of a sine 2 pi t? I know the power is a square by 2, correct? Now what is the square root of this? That will be a by root 2. So this is the RMS value of sine wave. RMS value of a sine 2 pi t. Okay. RMS value of the sine wave is amplitude divided by root 2. Have you taken down this point? RMS value is equal to square root of power. Shall I proceed? Okay, I'll give one problem for you to work out. I'll give one problem for you to work out. Okay. Shall I change the slide? Right. Okay. Can you find out the RMS value of this particular waveform? Find the RMS value of this periodic waveform. This is the waveform given to you. This is 1, this is 3, this is 4, 0, amplitude is 1. So question is find the RMS value of this particular waveform. I'll give 2 minutes for you to try this. 1 second. ക്ലാസ്സിലാണ്. Okay. So you can try in 2 minutes. Can you give me the answer? What is going to be the RMS value of this? So when you are asked RMS value, you just need to evaluate the power, take the square root. That's it. If you get the answer, you can unmute and tell me or type it in chat. So that will be 2 by 3 plus 2. Are you getting the answer as 2 root 2 by 3 or root of 8 by 3? Anybody is getting the answer for the RMS value? It's important to learn how you evaluate the RMS value of a signal, because mostly you'll be, yeah. Geshma got answer. Okay. I'll tell you how to quickly evaluate this. Okay. When you have any problem like this, it's pretty easy to find the RMS value. Let's see how we can see the find the RMS value easily. So I know this part energy is going to, sorry, RMS value, did I take it out of 8 by 3, 8 by 12, it will be coming, correct? Okay, 8 by 12, root of 8 by 12 is what you get, root of 2 by 3. Did anybody get the answer for this one? Yes or no? No. No. Okay. I'll work out. No problem. You just listen to it. I think the answer is going to be root of 8 by 12, something like this. Let us see. Okay. For this first triangle, we know it is equation is t, right? 0 to 1, the equation is t, because slope is 1, correct? So t square, root of 2 by 3 is correct, Karishma. So if I square it, that will become t square. Now if I need to integrate it from 0 to 1, that will be t cube divided by 3. And if I apply the limit, that is 1, 0. So it will be 1 by 3. Now, once I have the energy of this part as 1 by 3, I know this part will also have an energy of 1 by 3, because they are actually symmetric figures, correct? This triangle and this triangle will have the same energy. So both this energy will be 1 by 3. Now, to evaluate the energy of this part, it is very simple, because it is a constant part. The constant value is 1. Constant value 1, if you square, that will be 1 itself. Now, if you have a constant square, to integrate it, you just need to multiply by the width. You need not go for integration, correct? So because 1 to 3, 1 dt is equal to t applied from 3 to 1, which is nothing but 3 minus 1, 2. So 1 square is 1. 1 into width will give me the energy. So that will be 2. Okay. So my total energy will be 1 by 3 plus 2 plus 1 by 3. So total energy will be 2 by 3 plus 2, which is equal to 2 plus 6, 8 by 3. This will be total energy, right? Now total time is, I need to take 1 period's energy divided by 1 period time. So 8 by 3 is energy in 1 period, divided by period is 4. So that is 8 by 12, right? Which is equal to 2 by 3. Now the power of the signal is, power is equal to 2 by 3, correct? So naturally, what is RMS value? RMS value will be square root of power, correct? RMS value will be square root of power, which is equal to root of 2 by 3. So my answer is root of 2 by 3. Right. Root. Now, some more things about the power of any signal, right? This is the expression for power. I write down some more points here. Very important. Take down the one for any DC signal. For any DC signal, let's say K. DC signal means constant value. Power is nothing but power is equal to K square. Power is equal to K square. Right?
Hello sir, audible allala.
Audible alla? Not audible. Hold on. One second. Okay. Hello. 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 Okay. Hello. Hello. Audio miss చేయడా? Hello. 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 ഇപ്പോൾ audible ആണോ? Now? audible ആണ്, audible ആണ്.
അതെ
Okay.
ആ
Okay.
അതെ സർ അതെ സർ.
Okay. Okay. എന്താണ് പറ്റിയെന്ന് അറിയില്ല. I need to check this. Okay. Right. We'll continue. Okay. ജസ്റ്റ് ഇത് പറയാൻ തുടങ്ങിയപ്പോഴല്ലേ പോയിട്ടുള്ളൂ. അതിന് മുമ്പത്തെ കാര്യങ്ങളൊക്കെ ഉണ്ടായിരുന്നില്ലേ? പവർ നിങ്ങൾ ഓഡിബിൾ അല്ലാന്നുണ്ടെങ്കിൽ അപ്പൊ തന്നെ പറയണം കേട്ടോ. എനിക്ക് ഇവിടെ എന്താ പറ്റിയെന്ന് അറിയില്ല. റൈറ്റ്. ഓക്കെ. റൈറ്റ്. ഫോർ എനി ഡി സി സിഗ്നൽ കെ, the power is always equal to k square. Power is always equal to k square. Okay. For any DC signal k, power is always equal to k square. Right. Now, for any signal, any periodic signal, for any periodic signal, like suppose say if h of t is a periodic signal, with period or with power p, with power is equal to p, then x of t into u of t will have power equal to p by 2. This is an important point. Okay. I'll explain what is meant by that point. You can just take it down. If x of t is a periodic signal with power p, if you multiply x of t with u of t, power will be p by 2. I'll tell you what actually is happening. For example, suppose I consider this particular waveform. Okay. For suppose I consider this particular waveform. Okay. Then suppose I just make it one-sided. I know if it is extending from minus infinity to plus infinity, the power is P. Power is actually total energy divided by total time, right? Now, if I make it this is h of t. Now, if I make it h of t into u of t, as per the definition, total energy becomes 1 by 2 times the initial energy, because this side and this side is having same energy, right? If I make it h of t into u of t, this side is cancelling to 0, correct? So energy becomes E divided by 2. Am I right? But the total time is remaining the same. Total time is always from minus infinity to plus infinity. That is by definition total time. So total time is remaining the same, which means my power will be, actually it was E by T, correct? Now power will be E by 2 divided by T, which is equal to P by 2. This is the idea behind multiplying by U of T, giving you power is equal to P by 2. If your power was initially P, if you multiply any waveform with a U of T, then naturally power becomes P by 2. Is that clear? Is it clear? So that is one point which you need to learn about power. Now, okay. Suppose I give you an example. Suppose you are having h of t equal to u of t itself. What is going to be the power of u of t? Can someone tell me what is going to be the power of u of t? What will be the power of the signal u of t? What will be the power of the signal u of t? Can someone tell me the power of the signal u of t from this particular property? Yeah, answer is actually 0.5. How do you get the 0.5 answer? Okay, sorry. How do you get the 0.5 answer? See, if I have a DC value of 1, the power of that is k square, constant square. So that is 1 square, right? Now 1 into u of t means the power will be half, correct? So u of t power will be equal to, power of u of t will be equal to 1 by 2. Again, not audible. Am I audible now? 1 second. Am I audible now? 1 second. Yes. Okay. So the power of this particular signal is 1 by 2. U of t 1 by 2. Now there is one more important thing which you need to learn about power of energy and power. That is when you add up two signals. That is also very important. So we'll discuss that part also here. Actually, I'll write in this slide itself. The other slides are. Okay. Right. We'll see what happens if you add up two signals and what is going to be the resulting signals, energy and power. This is very, very important because we'll be using this property of signals to analyze it using Fourier tool. Okay. So the idea is, suppose I have a signal h1 of t. Okay. The h1 of t signal, I'm marking it as 0 to 2 with an amplitude of 2. Okay. Now I have another signal h2 of t, which is having another amplitude, let us say 3, and the duration is again, let us say duration I'm changing. I'll mark it as like this. Okay. So this part is 0, 1 and 2. Okay. And h3 of t is another signal which is having an amplitude of -2, -2, 0 to 2. Right. The idea is, if you just add up two signals h1 of t plus h2 of t, energy of the sum of the signals, is in general not equal to energy of h1 plus energy of h2. Okay. That is, they are not superimposable. which means if I find the energy of this signal can be easily found. Amplitude is 2, 2 square is 4, 4 into width. For any constant part, you can use this property. Square that constant value and then multiply by the width. Okay. So 2 square into 2, which is equal to 8 joules. So the energy of this part is E1 is 8. Energy of the second one is E2 is, see, this is 3 and this is also, this is minus 3. Okay. So if I square this term, 9 into width is 1, plus this term also squared, minus 3 square is 9, 9 into again width is 1. So 9 into 1 plus 9 into 1, energy of E2 is 18. Okay. Now what about the third signal? This part, energy E3 is equal to minus 2 square is 4, 4 into width is 2, again the energy is 8. Right? Now, the point is, in general, energy of H1 plus H2 is not equal to energy of H1 plus energy of H2. For example, if I consider the case where H1 plus H3, okay, if I add up these two signals, H1 and H3, the net result will be plus 2 and minus 2 will be added. So the net result is actually 0, correct? The net result is actually 0, right? So what is the energy of the new signal? The energy is actually 0, which is not equal to 8 plus 8. The first energy is 8, the second energy is 8. 8 plus 8 is not equal to 0, right? Whereas if I add H1 plus H3, what is going to be the result? What if I add H1 plus H3? Let us see what is going to be the new signal first. H1 plus H3, 2 plus 3, here it is 5, right? For the first unit, it is 5. So this is 5 for the first unit. Now, for the second 1 to 2, here it is 2 and here it is minus 3. So minus 3 plus 2 is minus 1. So I'll have the second part given by minus 1. Okay. So this is going to be the signal. New signal will be like this. 2 plus 3 is 5. For one unit, it is 5. For the other unit, it is 2 minus 3, it is minus 1. Right? So this will be the new signal. Now, what is the energy of this new signal? The energy of the new signal will be amplitude square into width. 5 square into width is 1, correct? Plus minus 1 is the amplitude in the second part, right? Minus 1 square, which is 1 into width is 1. So this is 25 plus 1 equal to 26. Now, what is the sum of energies? I got the energy E1 is equal to 8 and E2 is equal to 18. Now you can say 26 is actually equal to 18 plus 8, right? 18 plus 8 is equal to 26, which means this not equal to is not applicable here. If I am considering H1 plus H2, energy of H1 plus H2 is equal to energy, H1 plus H3, energy of H1 plus energy of H3. But in the case of, H1 plus H2, right? H1 plus H2, it is correct. H1 plus H3, it is not equal to energy of H1 plus energy of H3. So what can you say about this particular conflict? Did you understand why it is different? For the first signal and second signal, if I add up the signals, the energies will get just added up. For the first signal and the third signal, if I add up the signal, energy is not the sum of the energies. Now, what is the difference between these two pair of signals? For some particular case, this equation is valid. For some other cases, energy of H1 plus H2 is not equal to energy of H1 plus energy of H2. This is a very, very, very important relation for energy of sum of signals. Once the idea of this particular thing is clear, you can understand why orthogonality is very, very important. From the word itself, can you catch it? What is the peculiarity of H1 and H2 pair and H1 and H3 pair? Can someone tell me? You can unmute and answer the question. That's an interesting result, isn't it? Because this non-equal sign. Yeah. Can someone tell me the answer? Can someone tell me the answer for this one? Nobody?
Sir.
Yeah. So X1 and X2 are orthogonal to each other.
Yeah. And H1 and H3 are not orthogonal. That is the answer.
Yeah.
H1 and H2 are orthogonal to each other. And H1 and H3 are not orthogonal to each other. What is meant by orthogonality? I'll tell you what is meant by orthogonality. Okay, just 1 second. I'll tell you what is meant by orthogonality. Orthogonal means h1 dot h2 dot product will be 0. Now, in terms of discrete cases, you know what is meant by orthogonality. But for continuous signals, orthogonality is integral over h1 and h2 dt should be 0. For the case we have taken, this was the 0 to 2. 2 was the first signal, and the second signal was 3. This was one case, right? If you check this, you multiply and add these two signals. You multiply and add these two signals. You will get the multiply and integrate these two signals. The answer will be 0 because the first part positive into positive, correct? 2 into 3. For the second part positive into negative, correct? So this integral will be 0. That is why the signals are orthogonal. For the other case, one is this particular signal, the other is negative signal. They are not orthogonal because when you multiply and integrate, the result is not equal to 0. So that is an important point. I'll write that point. I'll just write that point here. Okay. So that point you should always remember. From that point, you can easily answer some of the problems for which will be asked in competitive exams. Okay. The point is for orthogonal signals. Okay, 1 second. For orthogonal signals. For orthogonal signals H1 and H2, energy of H1 plus H2 is equal to energy of H1 plus energy of H2. If they are not orthogonal, this becomes an inequality. They are not orthogonal, then this becomes an inequality. This is the point which you must remember. Is that very clear to you? And this is applicable not only for energy, applicable for power signals also. Applicable for power signals also. So that is one fundamental thing which you should learn about energy and power signals. That is, if you add up orthogonal signals, energy can be added up. Okay. If you add up energy signals, orthogonal signals, energy can be added up. Now, another important property along with this you should learn is all sinusoids of different frequencies are actually orthogonal. All sinusoids of different frequencies are orthogonal. Okay. All sinusoids of different frequencies are orthogonal. That is my next point. Okay. That is, if you have h of t given by h of t equal to 2 sine, let us say 3 pi t plus 4 sine, let us say 5 pi t. They are different frequency signals, right? But this signal and this signal are orthogonal. So what is going to be the power of h of t? Can you say what is the power of h of t here? Quickly. See, the power of this signal is 2 square by 2. 2 square by 2. Plus the power of this signal is 4 square by 2. Correct? So that is 4 by 2, 2 plus 16 by 2, 8. Answer is 10. Answer is okay. Answer is 10, right? Someone is telling 2. Is it 2? No. Amplitude square by 2. The power of this sum of the signals is actually sum of single signal's power. That is applicable only because this sine wave and this sine wave are orthogonal. Now, what about a sine wave and a DC content? If I add up a sine wave and a DC content, whether can I use the same principle? I'll just try to explain it with an example. H of t is equal to 7 plus 4 cos 2 pi t. What will be the power of this particular signal? Can someone answer me? What will be the power of this particular signal? You need to see to answer it from the fundamental relation or using the expression for power. It will take a lot of time. But you know the power of this particular signal 4 cos 2 pi t is 4 square by 2, correct? Which is equal to 8.
Am I right? Now the power of this particular 7 is, what is the power of 7? Shalini, are you giving you the answer?
49.
Yeah, it's 49. No, okay, right. 11.5, the answer for that is for another question, or which question Shalini answered 11.5? I did not get that. Okay, for this DC part, power is 49. For this AC part, power is 8. Now my question is whether you can add 49 plus 8 and write the total power is equal to 57. Is it possible or not? Is it possible or not? It is possible if and only if DC and sine waves are orthogonal. That is possible if and only if DC and sine waves are orthogonal. Now, what is your answer? DC and sine wave, is it orthogonal or not? If I just draw a sine wave, this is a sine wave, right? This is a sine wave, and this is a DC signal. What if I multiply and integrate? You can see for one cycle, for first half cycle, positive value into positive value. For the second half cycle, this is for the second half cycle, negative value into positive value. So this part integral and this part integral will cancel out each other, and the result will be 0. So any DC value, that is an important point. Okay, any DC value, any DC plus sine waves, any DC and sine waves are orthogonal. Okay. So I'll just list out 3 points here. The first point is, we will list out 3 points. First point is all, is it not visible? Okay. All sine waves of different frequency, are orthogonal. Okay. Second point is DC, that is constant signal. Okay, DC means constant signal. Constant signal and sine waves are orthogonal. Okay. Now the third point is same frequency, sine and cosine are orthogonal. So there are 3 points now. Same frequency, sine and cosine. Example is, let us say sine 2 pi t plus 3 cos 2 pi t. What are they? They are actually orthogonal because same frequency, but one is sine and another is cos. They are actually orthogonal. So the power will be 1 by 2 plus this will be 9 by 2. So answer is 5. That will be the power. Correct? So these 3 points you must keep in mind. These 3 points you must keep in mind. That is, all sine waves of different frequency are orthogonal. DC and sine waves are orthogonal. Same frequency, sine and cosine are orthogonal. 3 points are clear to you? So we'll just go through what we have learned for power signals and energy signals initially today, starting onwards. Energy and power signal, we have learned what is the expression for energy first. Okay, this is the expression for energy signal, and any signal, if its energy is finite, it is called as an energy signal. Any signal, if its power is finite, it is called as a power signal. Power is given by total energy by total time. We have learned how power can be different values. 0 could be coming, finite value could be coming, or infinity could be coming. If it's finite value alone, you can call it as a power signal. For all energy signals, power will be 0. For all power signals, energy will be infinity. Right? Now, summing up 2 signals, you can sum up the energy if and only if the signals are orthogonal. Another important point is RMS value is obtained as the square root of power. RMS value is obtained as the square root of power. So I knew this is a big topic because we need 1 hour to complete energy and power signals. Normally, I'll usually give more examples also. So we'll work out more examples and problems in the tutorial class. I need 1 more class to complete the systems classification. Maybe next Friday we'll continue during the same time. Do you have any doubts for this session? Except that audio break. Rest everything is clear to you? Clear. Any doubts? If you have any doubts in the in today's session, you can unmute and ask. Everything is clear for all of you? Okay, so I'll work out more problems in a tutorial class. Presently, we are just continuing with theory in the next class also. We'll classify the systems based on different properties. Okay, right. So we'll meet again on next Friday. Okay, tomorrow we'll have, I think, circuits class at 10 o'clock, right? Okay, so I'm stopping the recording. If you want, you can ask any doubt.